Okay, this is take number like 55. Okay, so I keep messing up, but just bear with me here. Okay, I'm teaching in front of a blank classroom. It's really awful. I'm trying the best I can here, so I'm just going to try to go ahead and jump right into it instead of giving a whole speech like I've been doing the last like 54 takes. But just know that I'm going to answer questions on this tomorrow. We're still planning on quizzing on this tomorrow. Okay, so this is going to be online on my webpage. You can rewatch it as many times as you want. You can skip around. But for right now, we're watching it as a class. Um, Also, all my notes are uploaded as well, so please check those online. Okay, please go through them and work through them and help each other out. You're going to have a homework assignment after this. I want y'all to talk with each other, help each other out, because you are going to be quizzed on this tomorrow. So please pay attention as I teach today, and please be patient with me, because it's really hard teaching a class with nobody here. I'm literally at the front of the class talking to nobody in the class right now. It's really weird. Okay, people are walking by, and yeah, I did this whole speech earlier, and the dang thing hadn't even started recording yet. So just bear with me. Okay, here we go. So yesterday we talked about Hamiltonian circuits and paths. We talked about how with Hamilton comes a certain type of problem, the traveling salesman problem. Okay, so we need to learn how those methods work, why it's important, all that good stuff. Remember with Hamiltonian circuits, it starts and ends at the same point, but it only hits every vertex once. We don't have to hit every single edge once. We're just trying to find the best route for a traveling salesman to start at A, go through every city, and then at A with the cheapest price. Okay. Yesterday we talked about weighted graphs, and we talked about completed graphs. So with traveling salesman, we're going to have a complete graph, and we're going to have the weights on those graphs. So let's refresh ourselves what weight means. In traveling salesman, the weight of an edge is going to be the cost it takes to travel from that city to the other city. So for example, the weight of edge AB is going to be 185. Okay, 185. That means that it costs Willie, I guess is his name, $185 to travel from A to B. We're going to assume in this example that it costs the same amount to go from B to A. So we're just going to assume that's the same both ways. The weight of edge EB in this case, so EB is $200. Okay, you can see that right here. All right. So let's just kind of go through. We'll find a Hamiltonian path, the Hamilton circuit. Then we'll talk about how to find the optimal path or circuit that we want really to take. Okay. So find a Hamilton path that starts at A and ends at D and give its weight. So let's kind of look at that right now. Starting at A and goes to D. Well, just any Hamilton path. We're not trying to find an optimal yet. So how about in this example, we'll say that he starts at A, and I don't know, maybe he goes, I don't know, A to E to D. Okay, that's a Hamiltonian path. It starts at A, ends at D. You don't have to go through every single edge. So that's A, E, D, with its corresponding weight of 133 plus 199, which, as I go over to my calculator and type it in, 133 plus 199 is 332. Any questions? Good. So as we go on to the next one, find a Hamilton circuit that starts with edge CD and gives its weight. All right, so I'm going to erase this bad boy right here. So a Hamilton circuit that starts with edge CD, so that's here to here, and it wants us to come back to C because this is a Hamilton circuit. How about in this example, we'll say C to D to B to A to E and back to C. All right, so C to D to B. If I can find that, there we go, to B. How about then to A, to E, and back to C. Okay, there's a Hamiltonian circuit. Its weight is whenever I add up all those numbers. 174, 150, 185, 133, and 120. If you add up those 1, 2, 3, 4, 5 weights, it equals 762. And you can check my math, but, you know, I'm pretty sure I'm right. So I'm kind of talking fast. Let me take a breather. I know you're taking notes right now. All right, the next one, it says find a Hamilton circuit that ends with edge EA and gives its weight. All right, it ends with edge EA. There's multiple ways this could work, but let's kind of draw one out. Okay, how about the example A, D, B, C, E, A? Okay, that ends with edge EA. What do you think of that? How about A to D to B to C to E back to A? So there's another Hamiltonian circuit. Well, there you go. If you add those numbers up, that weight, that's 152 plus 150 plus 121 plus 120 plus 133, which equals 676. All right? So, with these types of problems, okay, the graph model of a traveling salesman, if you look at this box right here, this is a pretty helpful box. All right, remember the sites are going to be the vertices on the graph. The costs are going to be the weights on the edges. The torr we're looking for, all right, those are Hamiltonian circuits. The optimal torr, that's the Hamilton circuit with the least total cost. That's what we're trying to find today. And we're going to talk about the methods in order to do that. So all this was kind of a review of yesterday. Let's look at the methods that we can use in order to find that optimal torr. So I kind of give you some examples in the real world right here that traveling salesman applies, not just with traveling salesmen, school bus picking up children, package deliveries, stuff like that. I'm not going to read through this right now with you, but just read over it if you want some actual real life examples. Okay. All right, so on to the first method of finding that optimal Hamilton circuit, that optimal path or tour that he takes to start at his city, end at his city with the least amount of money spent. Okay, there's two methods we talk about. The first one we talk about is called the brute force method. All right, brute force method. It's also called the exhaustive search, but we only call it brute force in this class. It is literally the only way to find an optimal Hamilton circuit is to actually find all possible circuits. Okay, so literally all brute force says to do is make a list of all possible Hamilton circuits. For each circuit in the list, we're going to calculate the weight of the circuit, and then from all the circuits, choose a circuit with the least total weight. That's your optimal torr. It's called brute force because an exhaustive search because we're exhausting ourselves going through every single Hamiltonian circuit and trying to figure out the one with the least weight. Okay. We got to check it one by one. It is very time consuming and is considered to be optimal but inefficient. Okay? Remember that. You're going to be tested on that. Brute force is optimal and inefficient. Optimal because it gives you literally the cheapest possible route. But it's inefficient because it's very time consuming. Okay? Very time consuming. Okay, so like I said, we got to list all possible Hamiltonian circuits. So in this example with Willie, this graph right here, okay, Willie has 5 vertices. How many circuits will we have to check? Well, remember our formula for yesterday. All right, we got n minus 1 factorial circuits in our graph. Well, we got 5 vertices. 5 vertices. So that's 5 minus 1 factorial, or 4 factorial, which equals 24. But remember what I talked about yesterday. Whenever we do that formula, all right, that 24 is 12 Hamilton circuits plus 12 mirror images. All right, we're going to assume that a mirror image is going to give us the same weight because we're going to assume that it's the same price backwards. So we don't have to check those 12. We only have to check the 12 regular images. Okay? So with 5 vertices, that can be kind of annoying, having to go through all 12 of them and list them all out, because that's kind of hard to just figure those out without accidentally overlapping or giving a mirror image. Okay, so we're checking 12. If you notice on the rest of your notes, I go ahead and give you those 12 to check. So let's go ahead and jump over there. So I won't expect you to take a completed graph of 5 vertices and actually list all 12, but I will expect you to list all of them for vertices of 4 or less. Okay, we're just doing this example to kind of understand how the method works. So we found all 12 of them. They're already listed in this chart. As an example of how it works, we're going to fill in number 2 together. All right, so that's the Hamilton circuit A, B, C, E, D, A. All right, and those corresponding weights are 185 plus 121 plus 120 plus 199 plus 152, which equals 777. All right, and remember, its mirror image is going to give you the same exact weight. All right, its mirror image is A, D, E, C, B, A. All right, so anyway, as we go through, we look at all the total cost, and we notice that the lowest one in this example is going to be number 11, okay? Number 11 with a weight of 676. That is the cheapest tour for this traveling salesman. It's cheap for him to go A, D, B, C, E, A, or we can give its mirror image A, E, C, B, D, A. On our test or quiz, I only really ask you just to give one of them. You don't got to give me the mirror image. We all know what the mirror image is. And its weight was 676. All right. Now it's brute force method. Not too bad, right? Let's do an example where we actually have to find our Hamilton circuits. All right, an example. This is the kind of problem you're going to see on your quiz. Okay, this exact kind of problem is what you're going to see on your quiz, so please pay close attention. It says find the optimal Hamilton circuit for the following graph. Use the brute force method. Write your answer using A as your reference point. Okay, so whenever we're starting at A, we got to end at A. So step 1 is figuring out how many we got to check. Okay, so remember our formula was n minus 1 factorial. All right, so we got 4 vertices, so 4 minus 1 factorial, which is equal to 6. So there's 6 Hamilton circuits, but remember, we're only going to check 3. Okay, we're only checking 3 because the other 3 are mirror images. All right, 3 plus 3 mirror. So that's why it's doable to do it with 4 vertices. You only got to list out 3 Hamilton circuits. All right, so I'll give you all 3 of them. Okay, the first one about A, B, D, C, A. All right, A to B to C, or D to C back to A. That is one Hamilton circuit. All right, go ahead and give its corresponding weights. We go to 10. All right, coming back down is a weight of 10. Going over is 7. And going back up is 8. All right, if we add all those together, that one has a weight of 35. Okay, if you want to write it out this way, it's fine. This was A, B, D, C, A. All right, my second one I'm going to check. I don't want to give the mirror image, so don't give A, C, D, B, A. That's not one. How about A, I'll erase this. How about A, D, B, C, A? There's one. All right, I'll draw it out. A, D, B, C, A. A, D, B, C, A, with this corresponding weights. 12, 10, 8, 14. All right, if you add those four weights together, it equals 44. A, D, B, C, A. All right, and then finally, the last one we can check in this example. What about going all the way around the box? So what about A, B, C, D, A? There's one. A, B, C, D, A. All right, with this weight, 10, 14, 7, and 12. Okay, those four weights add up to 43. So, of those three options, the one with the least weight is option 1. Okay? So my answer in this case is A, B, D, C, A. Or if you gave the mirror image in the example, that's fine too. A, C, D, B, A with a weight of 35. Okay? I'll pause for a second, let you kind of look at that. Let you think about it for a second. All right, I mean, that's the work I'm looking for, is that you can list out these three things and give their weight and just pick the one with the smallest weight. Okay, be able to know how to list out your three images. With 4 vertices, you only have to check 3. And then just find their weights, okay? Add up their weights. Notice how it starts and ends with A. Any questions? Good. All right, our next method is the nearest neighbor algorithm. All right, this is our last method with nearest neighbor, or with traveling salesman. I think y'all like this one a little bit more. Okay, go cheap. The brute force method takes too long for any vertices that are greater than 4. We saw that. With 5 vertices, we had to check 12. For 6 vertices, we're going to have to check 60 of them. Okay, that's ridiculous. It's brute force is doable for n is less than or equal to 4. We can check 3 Hamilton circuits in a completed graph of 4 or less. It's no big deal. But there is a faster method to come up with a good enough answer for anything greater than 4 vertices, 5 vertices, 6 vertices. Called the nearest neighbor. Let's read through it together. The nearest neighbor method. So all you're going to do is start from the home city where you're at. From there, you're going to go to the city that is the cheapest to get to. From each new city, go to the next new city that is cheapest to get to. When there are no more new cities to go back home. So all you're doing is just, you're not finding a bunch of Hamilton circuits and checking the cheapest. You're just going to find one. All right, the cheapest one to go to from each city. Let's do an example so you see what I'm talking about. Use the nearest neighbor algorithm, starting at vertex A to find a Hamilton circuit and its weight. All right, let's start with what the method says. We're starting at our home city of A. From there, we can go to E, D, C, or B. All right, but you're going to pick the cheapest weight. So So we got 133, 152, 119, 185. What's the cheapest weight from there? 133, no. 152. 119 is cheaper than all of them, so we're going to travel that one first. Okay? We're going to travel along that one. All right, then from C, we got to go to either B, D, or E. It's got 3 options it can go to. We're not going back to A yet. So of those 3, which one's cheaper? We got 120, 121, and 174. The 120 is the cheapest, so we're going to go all the way over to E. From E, it's either going to go to vertex D or vertex B. Which one's cheapest? The 199 or the 200? Will be the 199. And then lastly, from D, we only got one more vertex to go to before we go back home, and that's B. So go ahead and travel that way. Okay, and then B has to go back home. So there's my answer. I went A, C, E, A, C, E, D, B, back to A. Okay? If you add that weight together, if you add up all those numbers, that's, let's see here. That's 119 plus 120 plus 199 plus 150 plus 185, which equals 773. Okay, so I think it was a lot easier. We didn't have to find the many Hamilton circuits. We only found one. Notice that our answer, so this is the same example we did before with brute force where we had to check 12 of them. Notice that our answer is not an optimal answer, but the process to find is relatively quick. So that's the point of it. It's supposed to be quick. William Lohman has to decide if the time he saved not doing brute force is worth the money he loses from the difference. Okay? So we say that this is very important. We say the nearest neighbor method is efficient. That's awful F. I'm going to erase that. Efficient, not much better. And approximate. Know those 2 words. I will test you on that. So efficient because it's quick, and approximate because it's not optimal. All right, let's do an example. It says, use the nearest neighbor method to find the Hamilton circuit starting with vertex A, and then use it starting with vertex B. So we're starting with A, using the nearest neighbor method to find the Hamilton circuit starting with vertex A. All right, well, if I start at A, the cheapest route to go is over to B. It's a weight of 1. From B, I either want to go to D or C. The cheapest one would be to D with a weight of 2. Then we only have one place left to go, and that's C, and then back to A. So for A, my cheapest route was A, B, D, C, A, with a weight of 1 plus 2 plus 4 plus 6, which is 13. Okay? Now let's try it with B. There we go. All right, if we start with B, the cheapest route is to go to A with 1. From there, we're either going to D to C. All right, so we want to go to D because that's the cheapest weight of 3. Then we have to go to C, then back to B. So my answer there is B, A, D, C, B. That has a weight of 1 plus 3 plus 4 plus 7, which is 15. So notice that nearest neighbor is not the most optimal all the time. Okay, you are going to get a cheaper answer depending on where you start, but it is time efficient. That's the point. All right. Well, what if Willie Loman's territory gets expanded to 10 cities? How many Hamilton circuits are in this graph? You should know how to find it with 10 vertices. All right, that's 10 minus 1 factorial, which if you do it in your calculator is 362,880. All right, the number of edges on this graph. Remember the formula is n times n minus 1 over 2. So 10 times 9 over 2. It's 45. That is a huge graph. Okay, even with nearest neighbor method, that's annoying to have to start here, go through 10 cities, find a place. That is very annoying. Okay, so once we reach a lot of different vertices, a lot of cities, there is an easier way to approach nearest neighbor. That's our last thing we're going to go through next. Okay, I'm trying to keep this under 30 minutes. Okay, so the last examples we're going to do with nearest neighbor and done for today. So when we have a bunch of different cities, it can be too messy. A much more practical approach is to organize the data in a table. We're going to use nearest neighbor algorithm to find the Hamilton circuit starting at vertex A. All right, so this is how I approach this. This is how I read this table. I like to read it by columns. Okay, so for example, A, this is telling me the price it takes to go from A to B, from A to C, A to D, A to E, F, G, H, J, K. This is telling me those prices instead of labeling it on a picture where all the lines could mess up. Okay? So as we go through this, it says we're starting at A. Well, on this column, you're going to figure out of these values which one's the smallest one. We're using nearest neighbor. That's what we're supposed to do. So it looks like in this example, the smallest value is 119. So we start off by going from A to C. Keep track of that right here. All right, so then we go from C and look at its column, this column right here. We can go ahead and mark off A because we're not going to be going there, all right, because we don't go there until we end. So then go through all of these examples, all of these people in the column and see which one's cheapest. 121, 174. It looks like the cheapest one is then 120. All right, so if we're going from C to E, well, then you're going to go to E's column. Okay, so we then are going to check not A or C because we've already been to those places. Now see which one's the cheapest. So how about the 199? So that means we're going from E to D. All right, so now we're going to look at D's column. We've already been to A, to C, and to E, so we don't need to go back to those. The cheapest one then is going to be 150. So going to B. All right, so we're going to look at B's column. We can ignore A, we can ignore C, E, D, because we've already been to all those places. So now the cheapest one is going to be 379 at J. So we look at J's column. We can look, we don't have to go to A, we don't have to go to C, to E, D, B, or J. So the cheapest one we go to now is going to be going to city G. So going to G column, we're marking out A, C, E, we're marking out D, B, J, and that's it. So of those options, the cheapest one is K. So we go to K. Go to K's column. We're ignoring A, C, E, D, B, J, and G. I forgot to mark out G. Okay, so of those cheapest options, the smallest value is F. So I'm going to go over to F right here. And we have been to A, C, E, D, we've been to B, we've been to J, we've been to G, we've been to K. There's only one more city left to go to, and that's H. Okay, so I'm going to go to H. Now, if you notice, every single column has a number circled. So once we've reached every single city, okay, we look at H's column, and we're going to go back to A. That's how the method works. All right, so by the end of it, you should have numbers circled in every single column. Then, to figure out your weight, all you do is just add up those 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 numbers. So, I'm typing right now on my calculator, and sure, y'all should do the same. I'm sure everybody's just staring right now as I'm awkwardly typing this in. Should have done this beforehand. That's okay. I'm sure y'all love me right now. Or not. I'm getting 2153. Okay? 2153. Y'all can check that math for me. Alright? I know I'm over my 30-minute mark that I said I wasn't going to go past, but let's try this last example. It says the chart below represents the price of a bus ticket between the following cities. You want to use the nearest neighbor method. All right, and it says we're starting at, where are we starting at? Starting at the hometown of Z. We're starting here. All right, so as we look at Z, the cheapest place to go to next would be V with a weight of 45. So we started at Z, going to V. So as I go to V, we've been to Z. The cheapest one from there is X. So when I go to X, we've been to Z, we've been to V. Now the cheapest one between those two is Y. So when I go to Y, we've been to Z, we've been to V, we've been to X. All right, so there's only one place left to go, and that's W. We get to W, we've been everywhere else, so we have to go back to Z, which is a weight of 60. If I add up those numbers, 10 plus 60 plus 30 plus, crap, what's this, 37? Yeah, 37 plus 45, that equals, wait for it, wait for it, wait for it, wait for it, wait for it. God, I can't do math today. Yay, 182. Woohoo! Alright, I promise I'm done. Thank you all so much for bearing with me through this. Hopefully it all makes sense. Go back to these videos, rewatch them, go through my notes and read through them as well. I'll answer questions tomorrow on this stuff. Your homework's going to be posted on the board and should be passed out to you. I'll answer questions on that and we'll take it up tomorrow, okay? So, love you guys, good luck, and hopefully this wasn't too boring. It's really been awkward for me, I'm not going to lie. Alright, I'll see you.